BFT. Interestingly, the theory is nothing new. It is now very widely used for, indeed, distributed ledger systems, but previously, and this is still the case, they have been used for various types of distributed systems in general, or distributed real-time systems, for example, if there is a real-time element in them. We'll consider all those setups. A distributed system could be, I think we have briefly touched upon that even, let's say, an avionics system, which is used for aircraft control, where for redundancy, there are several, maybe 3 computational nodes interconnected by local or local bus, some kind of network which is placed on the aircraft, and they read information from sensors, process this information, and eventually maintain the state, obviously, and eventually output the orders to actuators. And it is very important, obviously, to make a consistent decision based on all those sensors, local computations, and so on, so that the aircraft is controlled in some kind of predictable, deterministic, uniform way. So originally, this research, which paved the foundations for BFT protocols, occurred long time ago. So that was 1982, when the original results were obtained by Leslie Lamport and his colleagues Shostak and others. We're going to discuss this original, very original setup first, and then see how this can be extended to modern systems. Interestingly enough, the principal results obtained in those papers of 1980-1982, they still stand. And for example, the maximum number of faulty nodes among the total number of nodes, which is less than, strictly less than 1/3, still applies. Let's see why this is the case and what is the original setup. So originally the problem was about a thought experiment, just some kind of idealistic setup, an idealistic model proposed by Lamport. So let's get back to, well, 1500 years ago, and imagine a situation that really it is a Byzantine Empire, which was, as you probably know, conducting continuous wars with all the neighbors. And so the military profession was very highly regarded in Byzantine Empire. So suppose that 4 Byzantine divisions are closing in on the enemy. Why 4? Is because really it is the simplest case to demonstrate the algorithm. So suppose that they're advancing on the enemy camp. And there are divisions, Byzantine divisions here. each one commanded by its own general. 1, 2, clockwise, 3, and 4. There is no single command. So this is a model indeed for a kind of decentralized system, which by the way was again quite typical for the Byzantine Empire, because the emperors typically distrusted, interestingly enough, the generals, and not allowed each general to become too much powerful or prominent, out of the fear that they could probably just dethrone the emperor himself, using their power and popularity with the troops. So there are 4 generals with roughly equal rights. So none of them is a commander of the other. They're independent, and nevertheless they need to make some kind of consolidated plan, because each division taken separately might not be able to defeat the enemy. So they really need to, although they are not subordinates of each other, there is no single commander among them. You immediately say, that's indeed our distributed ledger. They need to make some decision what to do. And to complicate the matter, first of all, what they do? They observe the enemy camp and make some kind of decision for themselves what to do. A decision is probably, just for simplicity, some kind of discrete variable. So, for example, it could have a 3 state, in the original Lamport's paper, even a 2 state value, but it doesn't need to be 2 state. And in his proofs, it was never actually used that the value is 2 state. The only thing which is required of this value is that it is comparable for equality, so any discrete set is okay. So possibly there are 3 values they can see. Attack doesn't say exactly when, just if attack, then let's say at sunrise tomorrow. They already know this by default. Attack, wait, or even completely retreat. That's the decision set. And each of them makes some kind of individual assessment of what to do. So we can see an immediate problem here, that even if the whole setup is correct and there are no faults, and precisely it's faults which this algorithm needs to conquer, it is a fault tolerance algorithm or protocol, but even in the absence of faults, it is very easy to see that, for example, 1 proposes attack, 2 proposes retreat, 3 proposes retreat, and 4 proposes an attack as well. So obviously the number is even, and therefore a deadlock in decisions is possible. So in this case, they can't make any decision. Well, each one makes a decision for themselves. We didn't even discuss how they would make a consolidated decision. You can already guess probably how. So they would let their own decision known to other generals. So each one has a message, is sending a message to all others, and similarly for all others, that's true as well, and so on, communicating their decisions to the others. Then everyone can build a vector, in this case of 4 entries, of what they and other generals are supposed to do. So, for example, one would get, well, in this case, all of them would get exactly same vector, A, R, R, A. And what? What kind of decision can they make in this case? Nothing. So the first element, which we'll later see, is indeed important in this protocol. How do you think this condition can be handled? Okay, they're equally split between two options. Everyone can see that they're split. What can we do in this case? So a majority value doesn't exist.
We need to add the condition that the consensus may only appear on odd amount of generals.
There are some good, yes, the consensus can only appear, well, the consensus can only appear in this scheme if there is a clear majority of the vote. So, for example, if number 4 suggests wait instead of attack, then probably retreat is the majority. Well, even if there are only 3 of them, then it is very easy to get the situation without a consensus. Each one proposes, the first one proposes attack, the second wait, and the third retreat. Even in that case, there is no consensus. You can only get a consensus with the odd number of generals if there is a binary choice. Otherwise, it is not guaranteed at all. So I think the situation is we must accept the situation when there is no consensus. And what would be the best way to handle the situation when there is no consensus? That's only one example how it may happen. There are some other situations, obviously, when the consensus can be reached. So no consensus, in the sense that no majority. What should we do? There is only one way actually I can think about. There is some kind of predefined default value which everyone applies in that case. No consensus, so default action. Obviously, out of these 3, the only safe default action is retreat. Obviously, if you use attack as a default, then you could very easily be defeated. There is no consensus at all whether to attack or not, so there are very serious doubts of whether the attack would succeed or not. If the default action is wait, then you are probably prone to the attack by the enemy itself. You wait in the proximity of the enemy, and it may very well be that the enemy would attack first. So the only safe option in this case is retreat. In real life systems, computer systems, we should also identify some least intrusive, most safe option of what to do if there is no consensus. Typically, it is known from the context of what the system is doing. So we assume that we are able to identify the default action. Well, in that case, everything becomes more or less simple. Either there is a majority value, so that what is the majority value? For example, we count the number of each values in this 4 vector. The majority one is the one whose count is really greater, strictly greater than any other count. Or if such a majority value does not exist, then the default action is applied. But that's obviously only the beginning of the story. The real problem here is that one of, and that's important, one of those generals can be a traitor. And we still need to handle the situation when there is a traitor. So let's call there is a traitor. In this case, for example, only one. Other generals are loyal to the emperor, so they're called loyal generals. So in this case, one traitor, but overall we can say M traitors, M traitors out of N generals. And it will be shown that the whole thing works if N is greater than or equal to 3 times M plus 1. Or put it another way, the number of traitors is strictly less than 1/3 of the whole number of generals. Like in this example, we can allow for one traitor, but in that case we need to consider at least 4 generals. So let's suppose that, for example, number 1 is a traitor. And what the traitor does might be very interesting. So what can it do? We already assumed that in order to make a consolidated consensus decision, the generals communicate with each other, right? They communicate by sending messages. So we must assume what kind of messages they would send. Even though there is a traitor, we assume that the capabilities of a traitor, well, his treacherous abilities, cannot interfere very much with the messages. So obviously he can send any messages to others. So for example, a traitor realizes that the enemy camp is vulnerable and he decides for himself and sends messages to others to retreat. That's entirely possible. Whereas others genuinely assess the situation. And by the way, in this case, it is very easy to get into something wrong. Let's see. So he would probably retreat for himself and send retreat messages to others. Furthermore, it is not impossible, and indeed it is very much the case which is considered here and which make the whole story interesting and complicated, that the traitor may, for whatever reason, try to confuse other generals and send to them, he cannot wait for their messages and see, for example, what is the forming majority of them, and then try to disrupt it. Let's say that they send all messages at the same time, with messengers, and then after a while, all these messages come and get collected and assessed. But not knowing exactly what other generals think, the traitor may try to increase the chances of confusing them by, for example, uh, what can the traitor do? Suppose that number 4 and number 3 decided to attack. Okay, the traitor doesn't know it, but he can assume that probably he's not the only one who actually realized that the camp is vulnerable. So probably there would be 2 others, that's quite likely, who would have a reasonable assessment to attack. Okay. What about number 2? The traitor doesn't know actually what would be the decision of yet another one. Someone, not necessarily 2, but someone who probably decides either to wait or to retreat. That's their own decision. So what would the traitor do in order to increase the chances of confusing the whole scheme? He can send, for example, a retreat to everyone. But then if number 2 decided to wait, then this retreat would be easily not easily, but nevertheless overridden by the majority of others. So what do you think the most treacherous action of the traitor could be in this situation?
For example, to send a message that is not the first option and is not the second option, so there is no majority.
Well, he does need to send a message with some clear specified option, attack, wait, or retreat. But in order to increase the overall probability of a confusion, he can send random messages to 3 others of wait or retreat. And in that case, increase the probability of a collision, I mean of his treacherous message to be uh, coinciding with intrinsic decision of one of 3 others, and that way it will be overall you can consider the probability state. Actually, in this probability state, sending random messages would overall increase the probability of no consensus, which would, for example, they know by default, in that case, result in the retreat. Okay, so that's what they can do. And it is actually dealing with those random messages is one of the objectives of this protocol. Interestingly enough, a traitor sending consistent messages is easier to handle by, actually, it can be handled by the same type of protocol which we have already seen. Whereas, well, in that case, there is nothing you can do. You don't know whether it is a traitor or not. He is sending consistent messages to everyone. If no consensus can be reached, then we take a default action. Is it possible that, in that case, the traitor succeeds in confusing the others and a default action is taken? Yes, of course, it is possible. But it is a normal outcome of this protocol, which does not differ much from the case when he is not really a traitor, but simply makes a wrong, genuinely wrong observation and communicate this value to all others. So we would say that it is really the intrinsic and important property of the traitor iterator sends a random messages to others, random ones, and this makes the situation much more difficult to handle. Uh, well, it is still possible. You see, why more difficult? You can ask, and I can ask you, okay, he's sending random messages. Why can't we apply exactly the same type of voting protocol? Either a clear majority vote exists, in this case the action is taken, or or it cannot be, and in this case a default action is taken. So what would be different? What would be different if the iterator really sends a random messages? What do you think?
Maybe it is possible that, for example, if the fourth general decides to wait and 2 hours decides to attack, the traitor may randomly send attack messages to the 2 generals which decided to attack, and wait message to general which decided to wait. And thus, it will, 2 generals will attack, while the third one will retreat, and traitor may do whatever he wants. So consensus will not be reached actually.
Well, it is quite possible that even if the iterator is not sending a random message, and then the consensus is not reached in some situations, simply because others are hesitating as well. And yes, this ARRA situation results in the consensus not reached. So that's entirely possible. You see that the principal difference is the following. If the iterator sends identical, let's put it that way, iterator sends identical messages to all. In this case, there is no way of detecting his iterator. Well, how can we determine whether he is a traitor or it is his genuine opinion to retreat, for example, or to wait? No way, right? No way to detect the treachery. This means that, yes, no consensus in some situations, and some of these situations can be caused by treachery. Some of them may be genuine, lack of consensus. It may, after all, be that, for example, the traitor decides to retreat, and others decide to retreat as well, genuinely, whereas 2 others decide to attack. So this may or may not be decided to the traitor's behavior, caused or not by the traitor, which results, and this happens with some probability p. So we can, obviously, in order to treat it strictly, we need to assign a probability space. So we need to say that, each of them makes, let's say, a valid assessment with a certain probability, or, for example, they make a certain assessment with equal probabilities, and then with some probability, there is no consensus. So how this probability can actually be computed, it is beyond this model. with some probability p. And then default action is taken with this probability. And that's probably okay. So now let's see clearly what the random iterator actions can result in. Identical, well, let's say deterministic. Identical deterministic messages. Iterator sends random messages to all others. One observation, as I said, and this can be proved by direct probabilistic computations if we do it rigorously and construct the probability space, is that the probability of no consensus increases. In simple voting, if we use the simple voting with default, right? Because he can, by sending random messages, increase the coverage of potential situations with no consensus. So from that point of view, this behavior is more dangerous. So more dangerous behavior, I mean, in the sense that more often we would have to shut down our system. What is the default action in a computer system? The default action is probably just to shut it down and to await some kind of a restart or manual interaction or anything like that. So more dangerous than deterministic treachery. But and that's a critical point. If the iterator sends different messages to each other, what do you think can we do? We can implement a multi-round protocol. We don't need to immediately perform a majority voting on the messages we received from everyone else. We can try to detect those inconsistencies. So ask others what kind of message you have received from others as well. So each of, let's say, loyal generals here, number 2, 3, and 4, can ask each other, well, they don't know who is disloyal and therefore ask number 1 as well. Not only, for example, number 2 is receiving all messages from 1, 3, and 4, but he is then asking number 1 which message that one has received from everyone else, which message number 4 has received from everyone else, and which message 3 has received from everyone else. And that way, it is possible to detect, how exactly we'll see now, detect inconsistencies in messages, maybe to figure out who is the iterator, or at least increase the chances of a consistent vote. So don't just perform a majority action on the messages you have just received. Ask others which messages they have received from each other, and maybe more than once. And this is the essence of this Byzantine consistency protocol. So each general I can ask others j from 1 to n, j not equal to I, which message j received from k. Again, k is 1 to n, k obviously not equal to j, and probably k is not equal to I as well, because although he may actually ask j which message they received from themselves, from I. If j is a iterator, then and it has an intrinsic random behavior, then I can even get back a message which he didn't send to k. So it may very well be that actually asking asking this for k equals to I does have a certain meaning, or including k equals to I. And what can we achieve in this case? At the cost of multi-round message exchange, even a single round of message exchange has quadratic complexity with respect to the number of nodes or generals. So a single round is of order n squared. Multi-round, as we will see, is of order n cubed. At the cost of multi-round message exchange, what do we do eventually? What would this protocol achieve? After all, consensus at every time? No, it will not. Clear isolation of a iterator? Might not, in some cases. What would this protocol achieve? What is the objective, what we're trying to do? What do you think? We simply aim at reducing the probability of no consensus. So there will be less cases, reduce p, less cases of default action due to no consensus. So once again, a random iterator compared to a deterministic one first increases the probability of no consensus if we are still using simple voting. But by applying this multi-round voting, we can exploit, make good use of this situation when there is a random behavior iterator, and on the contrary, not to increase but decrease the probability of taking a default action due to no consensus. So that's our objective actually. A very short break, a few minutes, and we'll continue. Okay, we are back to our Byzantine generals. Any questions so far? Anything not quite clear? All is fine?
Yeah,
Okay, then let's see what we can actually do in this situation. So, um, we want some kind of protocol which deals with this random, because apart from simple voting, there is nothing to do with deterministic iterator, all right? We need a more sophisticated protocol to deal with the random iterator. So before we design such a protocol, let us see what kind of properties it should possess. So what we are trying to achieve. Yes, overall we would say that way we'll reduce the probability of taking a default action. Okay, okay, but let us see what are the more strict, I would say, functional rather than probabilistic properties we would like to have from this protocol. And yes, the protocol is called um, at the cost of multi-round message exchange, and this multi-round exchange is indeed called our BFTP, Byzantine Fault Tolerance Protocol. Sometimes the treacherous node which sends random messages is called the Byzantine node, but I would not use this terminology. So if it is a general, we simply call him a iterator. If it is a computing node which sends random messages, we will call it a faulty node. Simply that. What do you think we would like to achieve? Um, let's see. By value v ij in some round r, it would be a value, a message, received by the first index is receiver, the second one is sender, r is the number of the round, received by I from j in round r. A treacherous node can not only send wrong messages about its own conclusions, its own intentions, but when asked by others which value they received, a treacherous node can propagate a wrong value because he's sending random values. A traitor can alter other messages, when propagating them, because the traitor, well, each node just sends some kind of new message, either the original assessment or a copy of a previous assessment from someone else. But mechanically, it is a new message sending, and of course, the traitor can send an arbitrary message in that case as well. Okay, so then Nevertheless, there are some properties of the messages which we believe, we assume that the iterator cannot affect. So still, message properties. Each sent message is delivered correctly. So a iterator can send a random message, but he cannot intercept messengers sent by other generals and alter a message. So a iterator, which means that in particular, a iterator can only alter. But what does it mean, alter? It means use arbitrary values. Messages it sends itself, including, however, forwards from others. But if it is ascending from I to J and the iterator is neither I nor J, then the message is received correctly. And in any case, the messages are not altered anyway. How could we make sure, using the cryptographic techniques we have already known, how could we ensure that each message cannot be altered in sending? So if a message is sent, then it is delivered correctly. What do you think? Using the cryptographic techniques we have already considered.
We can use digital signatures.
We can do a digital signature of a message. In that case, it is a little bit stronger property actually, because a digital signature would be obtained using someone's public key. And in that case, we also know who actually sent the message. And yet this is also a useful property. Not only the message is delivered correctly, but the sender of the message is known. Yes, this can be achieved by using digital signatures. One second, please. Okay, so this is indeed achieved by digital signatures. And yet another condition which is a rather technical one. It is possible that what is another thing a traitor can do actually? What are the possibilities? Okay, a traitor can send random messages. We already know this. What are other things a traitor can do? A traitor can simply send no messages. And in this case, what would happen? Uh, we have some kind of consistency or consensus protocol waiting for messages. The traitor is not sending messages. So absence of messages can be detected. Not because the messages are lost in transit. The first property actually guarantees that each sent message is delivered correctly, which means, first of all, it is delivered, and secondly, it is delivered correctly. It only means that in case a traitor doesn't send a message at all, and in that case, it is protected by, what do you think is a reasonable behavior? Okay, there are no messages, and what? We are defining a protocol, so what can we say how can we handle a situation when there are no messages? Typically, in real life systems, you have probably seen already some kind of message-based communication systems communicating by sending messages. So there is some mechanism which allows us to handle correctly the situation when there are no messages. Otherwise, if we don't do it, the whole protocol would simply deadlock, waiting for a message. The message is not coming. Obviously, the answer is by introducing a timeout and a default message in case of timeout. And default in case of timeout. It may or may not be the same value as we use a default action in case of a deadlock, but it might be a good idea. Not a deadlock, but lack of consensus. Same value as when no consensus. In our case, it is retreat. Okay, so these are properties on the messages. Now, what do we expect from our protocol before we define it? What do we expect from our protocol in terms of a kind of consensus we're trying to achieve? You see, it is very, I would say, unreasonable to expect anything from the traitor. So, protocol properties. You would probably agree that the protocol properties we are describing should only refer to which nodes or which generals? Loyal ones. Okay? Only, so the properties are only affecting the loyal generals. Why? Because a treacherous general can do whatever actually he wants. The protocol, he can completely even disobey the protocol, disregard all the values received, and do whatever they want, actually. So unfortunately, all consistency properties are only applicable to the nodes or generals which are really behaving consistently and obeying the protocol. Obviously, if a traitor can send random messages, then the traitor can also completely disobey the protocol. So there is no point in discussing what the traitor would do. The traitor can do anything. The traitor can even unreasonably go for an attack in order just to kill his division in a pointless offensive. So only for loyal nodes or generals. So the properties, there are two properties. Number one, if the sender J, the sender of a message J is loyal, then what? Then probably all loyal recipients must act on precisely this value. For all I which are also loyal, they should use. By use, it means use at each stage of the protocol. So use means if you need to propagate a message, then propagate it. If you use this message in taking your own final decision, then use it for voting. So propagate or use in voting. The value received from that loyal sender. Vij at each round R. And number two, let's see if the sender is loyal. Now suppose that there are two loyal recipients. Let I1, I2 be loyal recipients. What should loyal recipients do? Loyal recipients do not know whether the sender is loyal or not. They just get the messages. The only thing they can do is to use the value they got. So for any sender J, loyal or otherwise, they should at least use same values. Use same vi1j, vi2j in every round term. It may very well be that a loyal recipient will receive actually a wrong message from the sender J. But this is precisely the point which we would like to make. Loyal recipients consolidate the messages and somehow arrive at the same value. So this vi1j, vi2j might not be the value they received. They use same value. which makes not that they receive the same value. By use, we say propagate or use in voting at the final stage. So they must use same value, so obtained by some majority or default, if there is no majority. But all loyal recipients, they use some same value, whether it is an optimal one or not. Whether it is an optimal one or not, we don't know, because we don't know where this value came from. But still, it is some kind of consolidated value. Loyal recipients using this protocol consolidate the value coming from, the values coming from anywhere, and use consolidated values to propagate. And a loyal sender, in addition, that the difference between 1 and 2, a loyal sender, in addition, is guaranteed that his value is indeed used by all loyal recipients. So these are quite strong properties, actually. So basically, it means that in propagation, we may alter a value if the value is affected by some wrong value. But a loyal sender is guaranteed that his correct value will be used by a loyal recipient. These are the properties actually we want to achieve in the protocol. And now a very interesting way of how the protocol is designed. So far, it was a completely decentralized one, right? There are n generals exchanging messages. Now, to simplify the construction, Lamport, who is the author of this protocol, moves into a centralized argument. So instead of n completely equivalent generals, he considers a sub-problem. It is a problem of actually propagating a value from one of them. So a reduction, I would call it a reduction to a centralized case. We would really see that it is not a loss of generality. So a centralized case is that if locally, only locally, there is one commander, so instead of a full graph of communications, we now have some commander. And this commander has a number of lieutenants, L1, L2, and so on, L, for example, n-1. And the commander sends messages to them. The problem is any of lieutenants and the commander himself might be traitors. So it is quite possible that the commander is a traitor as well. So we still need to come up with a certain protocol among the lieutenants, which would make consolidated value for them if the commander sends a random values. Again, if the commander is sending just same random value, so same but wrong value, then there is absolutely nothing we can do here, and we are back to the original, very original case of voting. So if we define our protocol for this reduced case, so suppose that the solution exists. Which solution? Which allows the lieutenants to take a consolidated action in the presence of a random behavior of the commander, and do it in a better way than simply one-time voting. Obviously, simple one-time voting is always possible, but in this case, there is only one value they are receiving. So the simplest action would be just to obey whatever they received. It is not the case. So suppose that there is some kind of protocol which allows them to take a consolidated action. On the orders they receive from the commanders, and the orders are values. Then in a truly decentralized setup, if a solution to this sub-problem exists, so let's say this is a problem 1, and this is a totally decentralized one, which is a problem 2, our original problem. Then we use solution to problem 1 to solve the original one in a very simple way. So we take each of the nodes as a commander, and solve problem 1 with this node as a commander. So basically, this node takes its own assessment, and a consolidated action is taken by other nodes with this one as the first assessor. So basically, it sends orders to all, in this case, so-called lieutenants, use my value. Let's say 1, 2, 3, 4. And this is the first, or let's say even 0th round. So it says orders, use my value v1. At the same time, so 2, 3, and 4 take some consolidated action on this use my v1. After that, we can consider number 2 is also a master with respect to 1, 3, and 4, sending orders to them, use my v2. Can consider number 3, sending orders to all others, use my v3. And can consider number 4, sending messages to all others, use my v4. Then each node would, each group of nodes would take a consolidated action on each of these, and in a final round they would make a consolidated action on previously consolidated actions coming from other commanders. So that's a kind of divide and conquer approach to this protocol. So we consider its temporarily centralized way with the commander assigned by all other nodes, collect the corresponding values, and then do one more value of consolidation based on which original value has propagated from all other generals, which is, by the way, quite a non-trivial step. It is not so obvious that a fully decentralized problem can be reduced to multi-round centralized ones, as in this case. So it remains to consider problem one. So for problem one, the following algorithm has been designed, and then there is a proof that the properties 1 and 2, which we have set out, are indeed satisfied for this algorithm. So let us call it the first BFT algorithm, but there are really many of them. So the first original BFT. Obviously, the algorithm depends on how many iterators we have. In general, we have n generals, and strictly less than 1/3 of them are iterators. Why that? It is very easy to see that there is no way to develop the algorithm which satisfies properties 1 and 2 for 3 nodes in which one of them is a iterator. And generalizing this, we can show that if, for example, in the general case, there are m iterators and m is greater than or equal to 1/3 of n, then if such an algorithm satisfying 1 and 2 is available in that case, then we'll be able to solve it in the case of only 3 nodes. But in case of 3 nodes, there are very clearly defined counterexamples. We can't. So, by the way, it might be a good idea to show why it doesn't work in case of 3 nodes. Suppose that we have indeed 3 nodes. In this case, the commander, lieutenant 1, lieutenant 2. So what could happen is that a commander is sending, for example, the commander is a legitimate one, a loyal one, initially. He says attack to the first one. He says attack to the second one, obviously, because it is a legitimate one. Legitimate node sends equal values to other nodes. Which property is it? If the sender is loyal, then all other I loyal recipients receive and furthermore use the same value. That's property number 1 coming from the legitimate one. Okay, that's why obviously legitimate one sends the same attack to L1 and L2. But then they start asking each other which order you have received. So obviously L2 lies to L1 and say that commander said retreat, because L2 is a traitor. Or it is a possible situation that the commander is actually a traitor. In that case, let's say the commander still sends attack to L1, but sends retreat to L2. But in this case, L2 is a traitor, is a legitimate one. So he legitimately propagates to L1. Now we're looking at the situation from L1's point of view, that the commander said retreat. So what happens? In both cases, L1 acts on actually the same set of data, attack and retreat, but it is not possible to distinguish between these two situations. And what does it mean? It means that, so it receives exactly same data, and it means that for a legitimate node, L1, we have now the property number 2, that a loyal recipient like L1 should act on the same data coming from all other, all loyal nodes must agree upon the value coming from any other node, whether it is legitimate or not. In this case, it is not so. Loyal nodes in the second example are L1 and L2, and obviously because there are too few of them, only 2, with the commander being a liar, they simply cannot agree upon any value in that case, apart from obviously settling for a default one. This is actually a quite, I would say, artificial counterexample. You can think about a more, I would say, detailed explanation why it does not, no matter of exchanges, when we ask another node, what have you received from anyone else, would result in properties 1 and 2 satisfying for this exact case when there is one traitor out of 3. But if if there are more legitimate nodes, for example, 1 out of 4, and that is the minimum situation, then it becomes possible. So I will formulate the algorithm now, and we'll do more examples and more practical applications in, I think, next time, when we consider, first of all, the diagrams of how it runs over time, and secondly, we consider some practical implications about how many messages do we need to send, do we really need a full graph of communications, how to deal with delays, and things like that. So the first very simple case if m equals to 0, which means no operators. Then it is very simple. Commander sends values to each lieutenant. And each lieutenant simply uses the received value. Very simple. In case if we do allow, in this case, no value to be received as well, so for example, for whatever reason, but we have a property that all messages are delivered, so we don't consider this, then it would be a default value if no messages at all are sent. But we simply disregard this. So this is very simple. The real case if when m, and we'll call it BFT of m in general, when m is greater than 0, then the first step is the same. So commander sends its value, and we don't know whether it is a value same or not, to every lieutenant. Now consider a lieutenant number I, Li. Then, and the commander is, let's say, I is from 2 to n in this case. And the commander is obviously number 1 because it's a commander. Now, let vi1 be the value received from the commander, which li got from the commander C. Okay? It doesn't mean that he is using this value. What he does, now li acts as a commander to remaining lj. Lj, j from 2 to n, j not equal to I. And runs this algorithm, BFT. What can happen? Obviously, in how many iterators can we have? If the commander is a iterator, it may be possible. Then all other lieutenants are not iterators. Okay? If Li is a iterator itself, then there is no question about it at all, because it can do whatever he wants to do. And so this applies only to a valid one, because a not valid one can do whatever he wants to do. So in this case, he would run a BFT of m-1 algorithm with the over remaining j from 2 to n not equal to I, therefore n-2 are the lieutenants. So he acts as a commander to them. And then, as number 3, So as we did Vij, the value which Li got from Lj in step number 2 here. So he runs an algorithm and eventually got some value from them using this BFT of m-1 algorithm. So again, a legitimate Li uses Vij, set of Vij or default if there is no value. It might be that there was a traitor somewhere and there was no value, or default, and runs the majority algorithm on them. At each step of our algorithm, where the uppercase, I'm not running upper subscript R, would determine the depth of our recursion. And applying this majority, return the corresponding value to the caller. So that's how the algorithm looks like. On Thursday, we'll consider the detailed examples and the question of how communications work in this case. So for the moment, the most important thing to understand is that this algorithm is precisely dealing with random value sending iterators rather than consistent value sending iterators, because consistent value sending ones can only be dealt with by simple voting, and then all those complicated stuff is not necessary at all. But on the other hand, we can't increase, we can't decrease the probability of no consensus in that case. So let's stop at this point and we'll continue with examples and the real life implementations on Thursday. Everything okay up to now? Recursive algorithms are complex. Before we run an example, it is very difficult to see how it works. This is a formulation you can try for yourself before Thursday, and then we do the examples. Okay? Okay, if no more questions, we are done for now. Thank you.